I've already made a video that shows the sun stays the same size in a 3-hour window. I put a solar filter in front of the camera and I zoomed in. Then I took two pictures at two different times on that day and then counted the pixels. So I've already made that video. But one of the counter arguments from flat earthers as to why the sun would stay the same size if the sun is local and moving away from you is that they will claim it's due to something like atmospheric lensing. They've got all kinds of weird theories for that. And so here's the page on the magnification of the sun at sunset on the Flat Earth Society, and they give all kinds of reasons. So here's another one from the Space Center in New Zealand, and they basically describe what atmospheric lensing really is and how they figure how flat earthers use that to explain what's going on with the sun, and they also provide a number of reasons why that would not be the case. And I thought, well, one of the very real observations that we can make that shows how the atmosphere will scatter and absorb the light as the sun is farther away from us through things like water vapor. There's got to be a way that we can measure the intensity of the sun. So here's another one that explains atmospheric scattering and volumetric fog algorithms that they employ in games to give games a more realistic feel to it. So here are some real pictures, and you can see how the mountain in the distance is more washed out, and the definition of the colors is not nearly as great as it is as the mountains are closer to you. Then there's other things here. Here's another picture of another mountain. Here's, I guess, a damp, foggy evening, and you can see the light reflecting from the street lights. Here's another one. Here's the theory behind it. And here they start dealing with the games themselves. So this is a very simple and easy observation that everybody has seen. Just a bit of a quick explanation. I figured I was going to give a little bit of background, just so everybody understands what I'm talking about. If the sun is closer to noon, for example, and it's closer to you, I've drawn lines that show what the arc is of the sun when it's over here. And I took the exact same size of the sun and I moved it further away, and I drew the same lines on this side, and you can see that the arc is much smaller. So that, in a nutshell, is how something appears to be smaller as it moves away from you. Now, if we look at this on a flat Earth, so here is one observer that might be standing at 45 degrees latitude. Here's another one standing at 22 degrees latitude, and both of them have local solar noon. The sun is moving in this direction towards this observer. So when the sun is over here, it would be 9 o'clock in the morning from their local solar noon. And then as it approaches and gets closer to this observer's local solar noon, it would be moving away from these two observers. What can we use to describe what's going on here? Well, from this person's morning perspective, from 9 o'clock to noon, the lensing would have to decrease in effect to counteract the sun's increasing apparent size as it approaches local solar noon, so that it cancels perfectly. The sun is also increasingly going through less atmosphere because the sun is going to be closer to the observer at noon than it is at 9 o'clock in the morning, so therefore there's less atmosphere to go through. Conversely, for this observer at the same latitude, the lensing is going to increase in effect as the sun is moving away from this observer, and it's also going to go through increasingly more atmosphere. At the same time, someone who's at 22 degrees, the lensing is going to increase in effect more when they're closer to the equator, or the lensing has to increase more as they are closer to the equator, because if they are closer to the equator at local solar noon, then the magnification that has to counteract this shrinking sun as it's moving away from them is going to have to be much larger than for somebody who's over here. If this person was, let's say, 100 million miles away, then the distance from here to here in 3 hours would not be that much. You can think of it this way. The ratio of this distance from the sun to the observer at local solar noon to the distance of the sun at 3 o'clock in the afternoon to the observer is going to be different than the ratio of the sun to this observer at a different latitude when the sun is in the same position. So the lensing has to account for the individual at different latitudes. And the proportion is also changing different for different observers at different latitudes. So if we can take atmospheric lensing into account and say, okay, yeah, sure, the atmosphere is changing the size of the sun perfectly for every observer everywhere in the world all year long without any deviation, then there is the problem of atmospheric scattering. Now, the atmosphere will scatter the light in different conditions in greater intensity. You can see much farther on a clear day than you can in fog. So to that end, I decided to run an experiment. I got myself an app for my phone that measures the lux. I decided to point it directly to the sun throughout the day. Now, I did not want to swamp the camera of the phone out, so I used different material. Initially, I used tissue paper to just create a scatter, and I'll show some pictures of those materials and how I took those readings. And here are the results. So I did it on 3 days. August 24th are going to be these readings. By the time it reached 1 million lux, I figured that the tissue paper might not even be enough to block out enough of the sun that it would not saturate the phone. So I decided after the first 2 readings on the first day, I decided to try 2 other ways to measure the sun's intensity. I then tried just straight copy paper. I think it's like 24-pound copy paper. Then I took that same copy paper and I just let the light reflect off of it. And then on August 25th, I started to take some measurements, and then I got distracted with something else over here, which I will make more videos about. But I decided to finish this second day's measurements on August 31st by continuing at around the time that I left off before. So I kind of treat these 2 together as one particular day's worth of measurements. So then what I did was, I just loaded all of these into the spreadsheet. The times are rounded to something like 5-10 minutes. I kind of said, okay, it's close to, like, right now I'm recording this at 11:13 in the morning, so I figured, okay, this is going to be like 11:15. I didn't put the exact figures down, and I've also discovered that there are a few little oddities of the app that I used that kind of gave me some false readings, but I'll go over those. So the lux readings through the tissue paper sort of ramped up like this to about 10:25 a.m. And from about 10:25 to about 4:15, it tended to flatline. And then after 4:15, it started to go back down. Now, just in case that this flat line was because the camera was swamped out, and here you can see that there's a few outliers. This one here, I think, was one of the first ones. Yeah, so the ones that are in orange here were, I was using the maximum peak that the app on the phone gave me. So I was trying to go for the peak, and then at one point I realized that it would be better. So basically, all of the other measurements after this, I ended up just letting it use an average. But the problem is that I've discovered that it's a rolling average, and if there's a little bit of a burst of light, then it'll end up changing the strata that these measurements will land in, and I'll go over that in a minute. So, but you can kind of see that overall it increases, I would say, almost in a linear fashion, and then it flatlines, and then it starts to drop again almost in a linear fashion. Now, every single measurement that I've taken with either the tissue paper or the copy paper were pointing the phone's camera directly at the sun through those materials. The second type was through the copy paper, and you can see it's slightly different. So around 10:15 is when it kind of starts to flatline, and you can see, if you take away the one outlier, you can see that it tends to be relatively even in the same period. And of course, in the morning and in the afternoon, they start to taper off. Now, whenever I saw that it started to taper down, I kind of stopped because there was a tree in my backyard that would kind of prevent me from doing that. And then reflecting off of the copy paper, you can see that it ended up in two basic strata. Now, the reason why they are more or less the same readings are because I did not want to write it 6 decimal places down, and I just rounded it up to the nearest thousand. Generally speaking, I was after more of a trend than I was exact readings. So on 2 separate days, I was getting very similar results. I realized that the measurements I've taken have a few flaws, like the fact that the app tends to average over a certain period of time, that I didn't take the exact reading down to the lowest digit, that I didn't measure right down to the second. I was really after a trend more than exact figures, and I will probably end up revisiting this again several times throughout the year to see how the change in the seasons can affect those readings. Based on my initial measurements, that the sun stays relatively the same intensity for 6 hours in the day. This suggests to me that the sun is very big, very bright, and very far away, as described by the heliocentric model.